Hi, this is part two of machine generated text detection. Part one was on DetectGPT, kind of paper walkthrough and how the method works. Part two is on evading detection, deceiving machine text detectors through realistic red teaming attacks. This is the work that we did for my class on applied natural language processing. So I'm going to kind of walk through what we did and the results that we kind of concluded. And so we are focusing on machine text detectors, zero-shot detectors majorly, such as DetectGPT, DNA-GPT, DetectLLM, fast DetectGPT, and all that. And since they're zero-shot, they do not need any kind of training or examples or anything, and they should be able to work with the model, any LLM. Anyway, so the motivation for this work was this paper by Shi et al. So the paper was called Red Teaming Language Model Detectors with Language Models. And so they kind of proved that DetectGPT can be attacked by a word substitution. What they mean by that is that when you generate a passage by an LLM and then use random word substitution using another language model such as a BERT or a T5, a simple smaller language model, or a website such as just that kind of switches out the words from the text that you generate using an LLM. They proved that that is sufficient to kind of fool the machine text detectors such as DetectGPT, fast DetectGPT, and all that. And the primary point of concern that we had with all of this, because what happens when you do random word substitution is that there's a significant loss in quality and it affects the context and coherence and all of that. So the motivation was to kind of review the performance and robustness of these machine-generated text detectors and perform various red teaming attacks to assess their vulnerabilities in a more realistic, real-world kind of scenario and analyze the extent of the vulnerability while maintaining reasonable text quality. So that was the direction that we wanted to explore. And so the paper found conclusive evidence that word substitution attack greatly impact the performance of DetectGPT, however they overlook passage quality. Let's take a look at this example. So this is the direct LLM generated text, and this is the attack text that was used to kind of test the performance of DetectGPT. So we see white power converted to fat power, which left becomes which went away, 60-year-old becomes old major. Now, when you kind of look at these two passages side by side, it's gonna look the same, and you're gonna see, it might not look that much of a difference or a loss in quality or anything, but then just looking at this, it's gonna have a slightly different meaning. But then, in a real world scenario, when someone kind of generates a text and makes switches out a couple of words and makes some changes, they're going to kind of ensure that the quality is still maintained. They're going to ensure that the context is not affected. It's still going to sound like reasonably coherent and still going to make sense. And we just feel like this is affected by a random word substitution, and of course it is expected for DetectGPT to say that this was not generated by an LLM, because an LLM would not generate a sequence of words that is just unlikely for it. So the problem statement is that we present that detectors can be broken, also preserving the passage quality. And we extend our red teaming efforts to measure the impact of attacks on other detection methods as well, zero-shot methods as well. So the approach was to kind of take up 100 passage samples from the XM text dataset, and then we perform 6 different attack methods against each of the zero-shot method. So the zero-shot methods that we were testing were DetectGPT, fast DetectGPT, and DNA-GPT. And the samples, so the attack methods were random substitution, genetic algorithm-based substitution, which was kind of optimized specifically to beat fast DetectGPT. And then we add a threshold on top of this. So we were talking about log probability thresholds, log probability in the previous video. So we kind of applied a threshold to kind of limit the drop in log probability when performing these word substitutions. So at 0.2 and 0.4. So this ensures that when performing these word substitutions, either using random or the genetic algorithm, the log probability of the text with respect to the model that was used to generate it does not drop below 0.2 or 0.4. And this ensures that not too many words are changed, not too many substitutions are made, and it still kind of remains highly likely with respect to that LLM. And yeah, this kind of ensures that quality and context is not affected too much, We can take a look at some examples, and that should kind of help see that. So this is with random word substitution. So this the text on the left is the original sample, and then we have the random with no threshold and the random with 0.2 threshold. Let's look at some of the changes that were made. So there's a name change. Sunday becomes John, Heard becomes cleaned, and font becomes determined, which is fine. Survive becomes overcame, which is okay. Attire becomes onslaught, maybe not. Pulled away becomes directed aside. Yeah, this just sounds a little off. So market becomes mega store. They better cut it out becomes date advantages cut it out. So you see how these random word substitutions are kind of make it sound off and not as coherent sometimes. With the threshold, with the 0.2 threshold, we see that was just like a single word change. It would just change store. And we can see later how this still significantly affects the performance of DetectGPT on these thresholded random substitutions. Anyway, so we see how the generated sample, when we perform random word substitution with the threshold on the log probability, there's minimal changes, just single substitution. And this is an example with the genetic algorithm. There are a few more extra changes here. Let's check it out again. 60-year-old becomes golden ager. Found guilty. They were found guilty becomes found erroneous, which is, yeah, so again, it does not really make sense. And then many more changes that were made just to kind of just sticking to the genetic algorithm. Anyway, and then with the 0.2 threshold on the log probability, we see there were much fewer changes. It is still more than the random probability. But then, yeah, with the genetic algorithm, we see that the changes still make sense. They do not affect the quality or the context. And so now these attack texts were fed to the zero-shot detection techniques. And then we see their A or C scores on these different texts. All right. So this is on DetectGPT, Fast DetectGPT, and DNA-GPT. DetectGPT on the original still has like a 0.73, which is not great, but then Fast DetectGPT has 0.946, which is fine. We see how with random substitution, there's a drop from 0.9466 to 0.3, which is significant, which is what the initial paper by Shi reports on, and shows how Fast DetectGPT or DetectGPT is fooled by a random word substitution. But then we see how random word substitution with 0.2 as a threshold, which had just like a single word change store, right? Something similar. So all 100 samples would have had like a minimal substitution, and it still manages to kind of reduce the ARC score from 0.9466 to 0.6795, which is still significant. And then with 0.4, it drops further to 0.54. And then with genetic algorithm, we see a much more significant drop because 0.94 drops to 0.35, and then with 0.22, which is which shows how, you know, even with like minimal changes, we are still able to kind of fool these detectors, because that's what someone would do. They would kind of generate a text, makes just small changes here and there, and then it's still going to kind of fool these detectors and be able to pass as, you know, at least 50% pass as like, you know, human written. Okay. Future scope for this work. Test for a more generalizable attacking method. So instead of like just word substitutions, something else. Determine better techniques to assess the quality and context of text. So right now we kind of just assess this like manually, so human validation, and the laws of quality and context could be assessed in a more structured method. And testing the attack methods on different dataset domains. So we use the XM dataset. It could be tested on much more different domains and see how it affects that. And these are the references. So that kind of wraps up what we explored. This is what we kind of concluded, that, you know, we are still able to kind of fool these machine-generated text detectors while still maintaining quality with our attacks. And all right, so that kind of wraps up what we did. Thank you.